Good afternoon, everyone. Today we're going to prove a trig identity, and we're going to prove that this left-hand side of 1 over 1 plus sine x plus 1 over 1 minus sine x turns out to be equivalent to the right-hand side of 2 secant squared x. I'll give you a friendly reminder that 1 over cos x is how we write our secant x, and so by that logic, secant squared x is simply 1 over cos squared x. That'll come in handy a bit later on. So typically when we are dealing with these kinds of problems, we choose one side to stay the same, and we work to algebraically manipulate the other side for it to become the same as the original side, okay? Now, when I look at this problem, just intuitively, because the left-hand side kind of has more going on, and the right-hand side is just one term in and of itself, I'm going to choose to leave the right-hand side as it is and work to make the left-hand side become equivalent to it. And so I'll write 2 secant squared x a few times just to remind myself that that's what we're aiming for along the way, and we know that that's what we have to ultimately get to, okay? So now our task is to use some creative algebraic manipulations to have the left-hand side become 2 secant squared x. So it's nice to know where we are aiming to end up, okay? So when we look at our left-hand side, we see two terms added together, and they are both fractions. And so the first thing that comes to mind is getting a common denominator so that we're able to combine them into one term. So let's go ahead and do that. To get a common denominator, we multiply each fraction by each other's denominator over itself, because we are only allowed to multiply our expressions by 1. Because multiplying by 1 doesn't change anything, and we know that anything divided by itself has a value of 1. And so for the first term on the left-hand side, let's multiply by the other fraction's denominator over itself. And so by that I mean, let's multiply by 1 over sine x over 1 minus sine x. Again, anything over itself is equal to 1, and so this just means we're multiplying by 1, but creatively, right? And then conversely, our second term, we're going to multiply by our first denominator over itself, so 1 plus sine x over 1 plus sine x, like so. Again, any expression over itself is simply equal to 1, and so we're just multiplying by 1. Same idea as with the first term, we're just trying to be as creative as possible so that we can conveniently simplify our expression, okay? So let's continue. Let's multiply these through. So to multiply fractions, we know we multiply the numerators and multiply the denominators. So 1 minus sine x times 1 is, of course, just 1 minus sine x. And our denominators, let's be careful about how we write these out. When we expand 1 minus sine x times 1 plus sine x, this is kind of like multiplying by the conjugate. We'll have 1 times 1, then 1 times sine x, and 1 times negative sine x. Those are going to cancel each other out, right? Those are going to go away and disappear completely. And so there will be no sine x in our denominator, and we'll have negative sine x times positive sine x in the end, which of course produces a negative sine squared x, okay? Plus, now again, multiplying numerator by numerator, we get 1 plus sine x over, again, 1 times 1, 1 times sine x, 1 times negative sine x are going to disappear completely, so no sine x in our denominator whatsoever, and negative sine x times positive sine x means another minus sine squared x. And we know we're on the right track so far because we have our common denominator, which is what we set out to do. Now that we have our common denominator, we can go ahead and combine both terms into one and add our numerators. And so if we do that, we'll have 1 minus sine x plus 1 plus sine x over our 1 minus sine squared x. Now you can start to see the left-hand side simplify down a little bit, and you might start to see the direction that we're headed in. So 1 minus sine x plus 1 plus sine x means the sine x's cancel each other out with a negative and a positive, and all we have left is 1 plus 1, giving us 2 in our numerator. And in the denominator, we have this 1 minus sine squared x. Now, we could rewrite it as such, or we can remind ourselves that the very first Pythagorean identity that we learned in this chapter was that for any values of x, we have the result that sine squared x plus cos squared x is equal to 1. And from there, a tiny bit of algebra, simply subtracting sine squared x from both sides to convenience ourselves, gives us the result that cos squared x is equal to 1 minus squared x, right? You all see how that takes shape. And so with this result in mind, we can replace the 1 minus sine squared x in our denominator by its equivalent cos squared x. And so let's go ahead and do that. And now we have 2 over cos squared x on our left-hand side, and we know that 1 over cos squared x is our reciprocal identity secant squared x, and so 2 over cos squared x is, of course, simply 2 secant squared x, which is equal to our right-hand side of 2 secant squared x, and so our work here is done. Let's take a second to state all non-permissible values. In math, essentially what this boils down to is finding all values where we might be taking the square root of negative numbers. That doesn't seem to be anywhere in what we're dealing with. Whenever we're dividing by 0, or whenever we're dividing by something that is already undefined, presumably because we had already divided by 0, okay? So to avoid all those, we can't have either of our denominators be 0, and so that means that from the first term, we need 1 plus sine x to not equal to 0, right? And again, just doing a tiny bit of algebra here, that means that sine x cannot be equal to negative 1, which means that x cannot be equal to the inverse sine of negative 1, which means that x cannot take on any of the values where that is the case, and that is the case at, again, I'll remind you that sine of x is our y coordinate, and so when is sine of x negative 1? That's down at 3 pi over 2, and so x cannot be 3 pi over 2, and any integer revolutions worth around our unit circle either, and so we can write that as plus or minus 2 pi k, and so again, since we're having the plus or minus in the 2 pi k, we can restrict the k values to just be whole numbers, i.e. positive integers, to be a tiny bit more precise in our restrictions. Next, we also can't have our second denominator being equal to 0, which means that 1 minus sine x cannot be equal to 0, which of course means that sine x cannot be equal to 1, which means that x cannot be equal to the inverse sine of 1, which means that x cannot be equal to, again, our sine x is our y coordinate on our unit circle, and that has a value of 1 specifically at pi over 2, and any integers multiple of revolutions around the said unit circle, and so that means x cannot be pi over 2, again, plus or minus 2 pi k, where k can be any whole number. And finally, since this right-hand side is still part of our equivalency here of our identity, we also can't have any problems here, and since 2 secant squared x is really 2 over cos squared x, then we cannot have cos squared x being equal to 0 either, because that would cause an issue with the denominator of 0. And cos squared x being equal to 0, of course, simply means that cos of x cannot be equal to 0, right? Which means that x cannot be equal to the inverse cos of 0 in any way. And I'll remind you that on our unit circle, the cos of x is our x coordinate, and those are 0 at, again, pi over 2 and 3 pi over 2. And so in this very specific case, we've actually already accounted for all of those values, right? At pi over 2, that's taken care of in this part of our solution, and the other place that the cos of x has a value of 0 is down at 3 pi over 2, and all of those values are taken care of in this part of our solution. So we actually don't need to consider any more non-permissible values. we've already accounted for all of them. This set of values along with this set of values. And that is everything we need to do. So, we're done here. I hope this helps. I hope this starts to give you confidence in these trig identities proving, and I hope you start to see the pattern that emerges in these types of questions, the kind of creative little algebraic manipulations we need to do, like multiplying by 1 creatively, right? Getting our common denominator, multiplying by conjugates, all those things, so that we're able to manipulate one of the sides for it to become exactly the other untouched side, okay? And as always, do not forget your non-permissible values to be proper and complete, okay? Hope this helps. Thank you so much for watching. Have a great day.